All right, if you're joining us from the future, welcome. Hopefully not too far in the future because the exam is tomorrow. But so today will be a review session in which we go through any conceptual questions brought forward by students and talk through the equations introduced so far in class and what each part means, where they're useful, and so on. So hopefully today will be a pretty holistic overview of the things that we've covered in class, since a lot of it builds, but we'll be focusing on things that will be on or could be on free response quiz 2, which is basically lots of stuff from like interference up to very, very early, not electronics, electromagnetism. Yeah. Okay, so we've had a couple of questions already about the double slit equation. I'm going to go ahead and write that down. Does anybody else want to bring up any like general areas that are especially fuzzy? So I'll go ahead and write down double slit. So I'm looking here for what you might call like the muddiest point, the things that you thought were most weird. So a couple of concepts that I mentioned in the announcement. Where am I? Close that. Let me pull up the announcement real quick, just so I have that as my reference. Pardon me. Okay, bear with me one more second. Okay, so let me write these down. I'm gonna kind of pull you all to get a vote for where we want to spend the most time. So, whoa. Dude. All right. There we go. Let me zoom this up. All right, so what I want to do over the next few minutes here is just take some votes as far as which of these things are giving us the most trouble, which of them aren't that bad. In other words, just kind of figuring out where we want to spend our time for the next hour and a half or so. So what I'm going to do, it might take a second, but hopefully it'll be worth it, is I'm going to ask y'all to react to each topic, okay? And I'm going to take about five or 10 seconds to react on each topic. So get ready with the thumbs. Okay, so you can vote as many times as you like. I'm going to clear responses after every vote, but if you want to spend some time on interference, like in the sense of phase difference diagrams, go ahead and give me a thumbs up now. Okay, and let me find those. Okay, thanks. That's probably around like 15 or so, 15, 20. Okay, how about I'm going to clear responses. Okay, how about for beats? Who feels like beats could be a good place to spend time? Thumbs up, thumbs up, thumbs up. I'm seeing 5 so far. Okay, we'll let those clear out. Okay, who's feeling diffraction? Where's my diffraction crowd at? Diffraction as a place to spend time. Okay, I'm seeing 17. Okay, how about standing waves? Where's my standing wave people? And remember, you can vote as many times as you like. Standing waves, I'm seeing roughly 15, 16, 17 there, okay. Okay, quantum mechanics crowd. Send me your votes, send me your thumbs. Okay, quantum mechanics is a pretty clear winner. That's all right, good to know. Okay. How's about mirror optics? Mirror optics. You're like, yeah, after lenses, mirrors aren't so bad, right? Okay, so I see 4 for mirror optics. Snell's law, the bending of light as it enters a medium or exits a medium. Snell's law, I see 10. Okay, lens optics, including multi-lens systems, yeah, the mirror lens equation, magnification, and so on. lenses, I see 6 or so. Okay, and last one, qualitative descriptions of electric charge and force. 18, 20, somewhere in that range. All right, all right. Okay, good to know. So we can spend some time. It looks like the
Wait, for the last one, it says 26. I thought it was 18 to 20.
One more time.
For the last one, which has 26, I thought you said it was 18 to 20.
Yeah, it boosted up as I said that a little more. Yeah, so I had to edit back. Okay, but thanks. Good catch. Okay, so it looks like places where we want to spend the most time are quantum mechanics. This is our number 1. Then electric charge and force. Diffraction, standing waves or tide. Then interference. Okay, and Snell's law. Okay, so mirrors and lenses we're comfortable with, beads pretty comfortable with. So what I want to do, I think, is let's start off, because there's so many people who are asking for it and because it's less connected to many of the other things, let's start off with quantum mechanics, and that'll segue us nicely also into standing waves. So we'll start off with these two. We'll knock those out and then move on from there. Sound good? With me so far? Okay. So let us pull. I'm going to pull the relevant equations for these. So first, let me just write them. So we'll start with quantum mechanics, and I'll kind of backtrack a little bit to talk about standing waves. Quantum mechanics. We've got basically two main concepts that we want to emphasize. The first is there are quantized energy levels associated with standing waves. Okay, now what quantized energy levels means is that the energy levels, the energy of the system, instead of being continuous, like instead of being, 1 joule, 1.1 joule, 1.0001 joule, etc., it comes only in discrete chunks. Like you have to make a jump from one level to the next. That's what I mean by quantized, is that they come in discrete jumps instead of being a nice smoothly varying curve. So an example of energy which is not quantized is like your typical kinetic energy, 1/2 mv squared. So if I have something that looks like this, 1/2 mv squared, well, velocity can be any real number, right? It can just be any old number you pick, rational, irrational, whatever. Velocity can be any old number. So the kinetic energy also can be just any old number. It varies smoothly with v. So if I have v here and the energy on this axis, it varies smoothly. It just makes a nice little parabola. Quantum is a little different. There are only particular discrete energy levels associated with n, let's say, and n is just some integer. So here it's like I have particular points where I have allowed energies. There's nothing kind of like spanning this gap between energy levels. Sorry, this is an energy axis. Always be sure to draw on your energy axis. Okay, so that's the first thing, quantized energy levels. All right. The second one is photon emission. Photon emission, which is closely related to the hydrogen emission spectrum, but whatever. So, or I'll say photon emission / absorption. Okay, so the basic idea behind photon emission and absorption is this. When a quantum system, in real life, it's usually like a single atom, say, but when a quantum system moves from one energy level to another energy level, when it changes states, I'm going to call this the n = 1 state. And here's the, let's say, n = 4, n = 3 state. When it changes states, one method for doing this, one mechanism for absorbing the energy it needs to go up from the lower energy to the higher energy is by absorbing a photon. So a photon, which is a particle associated with light, it's like the basic particle of light. A photon comes in. This is the photon, this little squiggle. It kind of like hits the quantum system, and is absorbed. So the energy associated with the photon is absorbed into the quantum system, causing the energy level to increase. And in my head, I kind of think of that as like spreading the quantum system out more. It makes it kind of like bigger in a sense. But that's just some intuition that I have built on top of the math. So there's no need to like share that intuition if it's not intuitive for you. Oh, there's a question to get a link to the Zeitboard. Yes, here it is. Okay. All right. Welcome, welcome. Okay, so here we are. Let's see. Sorry, killed my own train of thought there. I'm a bit slow today. I don't know if I can tell. I didn't get as much sleep as I should have, and then I coded for like 6 hours, which is just zonks you out. Okay, so let's get back on track. So those are the two key ideas. Quantize energy levels instead of the energy continuously varying with some discrete variable like v, velocity, and kinetic energy. Instead, it comes in discrete jumps with an integer n. So it skips over some intermediary energies. The other thing is photon emission and absorption, which is the mechanism by which quantum systems that we're interested in change their energies. So you dump in some energy in the form of a photon, that energy is absorbed by the quantum system and it boosts up to a new energy level, or vice versa. An energy level or a quantum system at a higher energy level, say the n equals 4 state, can drop down to a lower state, say the n equals 1 state. And when it does that, you emit a photon. That's where the energy goes. So the photon kind of acts like it's like a truck for the energy. It carries the energy in, or it carries the energy away. I don't know if that's a useful metaphor. All right, so those are the two basic ideas of quantum. From those two basic ideas, most other things follow. Do we have any quick questions while I'm here? And then I'll break down the equations too. Real quick, let me get some thumbs. If this is, well, let's do it like this. If this is a good speed, give me a thumbs up. If it's too fast, give me an open mouth. And if it's too slow, give me, I don't know. What's a good one for too slow? Is there a thumbs down? There probably isn't. If it's too slow, give me something else. Anything else, and I'll just count it in my head. Crying face looks good. Let's do that. Okay. Okay, good to know. All right, sounds good. So we'll go a little faster probably. Maybe around the same. Okay. Let's get over to the equations then. So there are a couple of equations that are useful in quantum. Let's start with the one that's maybe a little bit faster first. The first is just a restatement of something that we already know, which is that the wavelength or the speed of light c must be the wavelength of a photon times the frequency of that photon. Okay, so this is something that is, well, I suppose it's speed of light in the medium. So really, this is the speed of light wherever it's velocity. It's the, cool. Okay, let's back it up. The general statement is this, all right? The velocity of a wave is the wavelength times the frequency. Now, if it's a photon traveling in a vacuum, for a photon in air / vacuum, that speed, the speed with which the photon moves, is just the speed of light c. Then c is the wavelength of that photon times the frequency of that photon. Okay, from this, and from some other calculations that I won't bother with too much here, we get that the energy of a photon, which is HF, can be rewritten as hc over lambda. So this is a good one to box, good one to understand. Now, what this tells me, what this equation tells me, is that if I have a single photon, a single particle of light, its energy is a function of its wavelength. H is a constant, C is a constant, so the energy of this photon is constant. However, sorry, not the energy of this photon is constant. For a given wavelength, the energy is constant. In other words, like a photon's wavelength determines its energy. There we go. That's probably the best way to say it. So as it happens, Hc is 1240 electron volts per nanometer, or electron volts times nanometer. So if I know the wavelength, it's really quick to compute the energy as in units of electron volts. So Hc, this thing on top, is roughly 1240 electron volts times nanometers. And that's something that we'll provide on the exam too. Okay, what else? Okay, the energy that is supplied to one of these quantum systems when they do a photon emission or absorption is just the energy of that photon, right? So when we're thinking about absorption and emission, this is an important formula to keep in mind. This is the energy of a photon for a given wavelength of that photon. And to encode what I just said in an equation, the change in energy of a quantum system must be equal in magnitude to the energy of a photon. So the magnitude of this energy change is equal to the energy of a photon when we have a photon emission or absorption. So what that means is that, the change in energy, so if I go like for a quantum system E5 to E2, this tells me that a quantum system has moved from its 5th energy level down to its 2nd energy level. The photon energy, or vice versa, sorry, that would be final minus initial, we'd be going from 2 to 5. The photon associated with that transition would have that same energy. This allows me to cleanly transfer or translate between a known change in energy of a quantum system and the wavelength associated with that photon, the photon that carried the energy in or out. I want to take a second here and ask if there are questions, because I think this is one thing that tends to be a stumbling block. And let me pull the chat up. Feeling okay? Thumbs up if you're like, I'm all right. Open mouth if you're like, meh. And crying if you're like, is it crying with joy? What is it? And crying if you're like, I have no idea what's going on. Please help. Okay. All right. Mostly thumbs up, a couple of mehs, a couple of AFKs. That's how it is. All right. I see you. All right. Can I repeat the last part again? What are the numbers on the E's? Can we apply this to an example? Yeah, sure. Okay. So I see there's a little bit of questions still. That's good. Okay. So what are the numbers on the E's? So I just kind of picked arbitrarily some numbers, but this is a 5 and a 2. I'm saying if I were to transfer from the n equals 2 energy level to the n equals 5 energy level, that would be associated with some energy of a photon. But really, this is just to be more general. It's 2 different indices, m and n. So these are both have to be integers. There are 2 indexes, but they can be any positive n or m. Another question, is photon energy always positive? Yes, it is. Good question. So one way that you can kind of see that just from math without physical intuition is that wavelength is always a positive number, and H and C are both positive. So the photon energy is always positive. However, it's not like necessarily apparent without that, but yeah, it turns out it's true. There's another question that says, can you read the last part again? So I have these 2 relationships. One tells me the energy of the photon as a function of its wavelength. One tells me the energy of a photon as a function of its wavelength. The other tells me about the energy of a photon as it relates to 2 different quantum states, i.e. The 2 states that a quantum system has moved between. So say it absorbs a photon and moves from energy level n to energy level m. That also tells me the energy of a photon. I think it is true that an example could help. So let me introduce the first quantum system and the one that you most commonly see. Well, tell you what, let's mix it up a little bit. Let me write down all of the quantum systems we've looked at first, and then we'll do kind of like a little baby practice problem with photon emission. Okay, so if I had, for example, no, let's just write them. I'll write them. Okay, I'll stop waffling and just write. So the energy associated with the quantum harmonic oscillator, QHO, or just harmonic oscillator, this is the spring-like thing. Maybe two atoms bound together. Quantum harmonic oscillator, it's like a mass on a spring is the idea. The energy associated with it is given by 2 times some baseline energy, the ground level energy, times, it's n plus a half. What is it? Yeah, it's n plus a half. N plus 1/2. Okay, now what does this tell me? First of all, notice that if I pick n equals 0, I just get that E0 is equal to E0. So I set some baseline energy, E0, and from that I can determine the next couple of energies. The next energy would be what? 2 times E0 times 1 plus a half. That's 3 E0. E2 is, let's see, 2 times 2.5, that's 5 E0, and so on. Okay, so this is the harmonic oscillator. The hydrogen, let's do particle in the box. The particle in a box, the idea here is just that it's a particle that's confined to move back and forth between 2 walls forever. So it's a particle in a box. And its energy levels, I'm going to relabel these just as En so that it's clear. Okay, this is particle in a box. Its energy levels are given by, is it 8ml squared? Yeah, okay. N squared H squared over 8ml squared. So the N here is just another index that runs from 1 up. So N equals 1 or more. Importantly, for the harmonic oscillator, N starts at 0. So the harmonic oscillator has its ground state, N equals 0, and the other two are going to have ground states be 1. Double check myself on that. Yeah, that's right. Yep. Okay. So the ground state energy, the first state for the particle in a box is just H squared over 8ml squared. The second is 4H squared over 8ml squared, and so on. So these are, again, discrete energy levels. Getting back to our first point, the particles, the systems can only have particular energies and not any energies in between. Kind of going back over to this image. Instead of varying cleanly like kinetic energy did with some continuous variable like v, velocity, instead it varies discretely with some like integer-like variable n. Okay, boom, particle in a box. So the n here is an index that's associated with like a standing wave. Here's the n equals 1 standing wave, here's the n equals 2 standing wave, and so on. The h is Planck's constant, which is just some constant that we give you. M is the mass of the particle, mass of the particle. So this particle is moving around in our box, right? But the particle has a mass. And L is the length of the box. There's L, the length of the box. So those are the energy levels of a particle in a box. Finally, we have a hydrogen atom. The hydrogen atom has energy levels of, it's negative 13.6 eV. Yeah, that's the binding energy of hydrogen, right? Yep. Times Z squared, where Z is the number of protons, divided by N squared, where N is just another index. For this system, N starts at 1. So for the particle in a box, let me complete our little table here by writing, this is the hydrogen atom. Pardon my chicken scratch. So for the particle in a box in the hydrogen atom, n starts at 1 and then goes up as the integers. For the harmonic oscillator, n starts at 0 and goes up as the integers.
For the particle in a box, isn't it when you have two fixed ends?
That's right. That's right. It's the standing waves are equivalent to when you have two fixed ends. Yep.
And it doesn't work with a fixed end and an open end, right?
That's, oops, we've got 1 second. That's right. Okay, we don't have mirror view. That was a weird glitch. So that's right. There are a particle in a box that had like one open end would mean that there like wasn't a wall here or something. I don't know. So it wouldn't be in a box anymore. So yes, the particle in a box obeys two ends fixed. The two ends fixed rule for standing waves, which is to say you get like half a wavelength, then 1 wavelength, and 3/2 wavelengths, then 2 wavelengths, and so on.
So like n equals 1 would be a fundamental one, right?
Yes, it's this one here. The one with one antinode.
Yeah.
N equals 2
n equals 2 is
this one.
Second harmonic, is that what it's called?
I'm gonna avoid using the language harmonics typically, just because it gets so tricky. But I'll usually say it in terms of like the fundamental would correspond to this one, and then the one above the fundamental would be this one. The one removed, 2 removed from the fundamental would be the next one, and so on. Yeah, so I'll try to be extra explicit if we have that kind of thing. Yeah, it should be pretty clear, and I'll try to use very unambiguous language. Yeah. Okay, so these are the quantum systems. These are the ENs. So if I had, for example, a harmonic oscillator somehow, some quantum harmonic oscillator that moved from the n equals 5 state to the n equals 2 state, and I wanted to know the energy of a photon produced by that change, I would go over to this equation. If I was then interested in the wavelength of that photon, I would take that energy of a photon, pull it over here. Yep. So there's kind of like a 2-second mini example. I would calculate each of these photon energy, each of these En for my harmonic oscillator. I'd say, what is E5? What is E2? I would plug those in on the left-hand side of this equation. That would let me know the energy of the associated photon. Okay. Anything else here? Oh, there's a question coming in. I remember from an old practice quiz, the formula for the quantum harmonic oscillator was En plus 1/2. Do we need the 2 in front of E? Yes. So that old practice quiz probably was, there are kind of different ways you can write this based on basically whether you want to include that 2 inside of E naught. And we're going to leave it off. Yeah, so we'll include the 2, and that'll be represented on the equation sheet. Thanks for the question. Okay, so we've spent around a third of the time on quantum, which I think is probably just about appropriate. Are there any wrap-up questions on quantum before we move on? I'll talk about standing waves here in just a moment. I'll chill out just in case there's any chats coming in. Take a nice drink of water here. 1 sec. Okay. What is Z for the hydrogen atom equation? Good. So Z in the hydrogen atom equation, this is the number of protons of a hydrogen-like atom. Number of protons of a hydrogen-like atom for our hydrogen-like atom. So the basic idea here, like from a physical type perspective, is that the more protons I have, the stronger my electron is going to get pulled in by those protons, right? Because I've got multiple positive charges and a negative charge from this electron. So the energy required to pull that electron further away to change the hydrogen atom state gets larger the more protons I have. So Z is the number of protons for a hydrogen-like atom. And what hydrogen-like atom means is just that there's only one electron and not too many neutrons, whatever that means. Yeah. Good question, thank you. So yeah, so for example, like if you had helium that was missing an electron, that would be a hydrogen-like atom with Z equals 2. Okay, real quick, review of standing waves. Ready? Woo! All right. If you didn't like quantum and that wore you out, grab a cup of coffee, come on back. Here comes the standing waves. So there are two kinds of standing waves that we're interested in here. Two ends fixed and one end fixed, one free. So when we say this word fixed, what we mean is that we put a node there, node at the ends. So standing waves with two ends fixed come in a variety of lengths. We need to put nodes here at this end. So let's put this, I'm just going to call this length L. The first I won't call it first harmonic. Oof, again, getting too used to the language. So the first one associated with n equals 1 is this one. Second harmonic, which I called, slipping up here, calling it harmonic, but whatever. The n equals 2 corresponds to 2 antinodes. N always is the number of antinodes in here. Looks like that. Notice that I've drawn it this way because I need both ends to be fixed. I need both ends to be nodes. The n equals 3. Something like that. N equals 3, and so on. Okay, so the relevant equation for thinking about the allowed wavelengths of these standing waves is lambda n equals 2L over n. Boom. Hopefully this makes some sense, right? So when n equals 1, our wavelength is 2L. So the amount that fits inside a length of L is a half wavelength. When my n is 2, my lambda is just L. So I have one wavelength fitting inside my box of length L. When n is 3, I have a wavelength of 2L over 3. So I have 3/2 of a wave inside my L.
Will this equation be given to us?
Yeah, this one? Yep, you got it. I see a chat coming in. Let's see. Okay, hopping back for just a minute. Brittany asks, can you clarify in which cases we use the different En equations again? So the one on the far left here, En is 2E0 n plus 1/2. That's for a harmonic oscillator, which corresponds to like, say, a diatomic molecule or a spring mass system, a quantum spring mass system. Will usually be pretty explicit. Yeah. Particle in a box is the central one, which refers to it's really basically just a theoretical thing, but it refers to a particle which lives in a space that's confined to that it can never break out of. So it's really is just stuck moving in a line back and forth like this between two infinitely hard walls. And the last one is the most realistic one. This is the energy levels of the hydrogen atom, a hydrogen atom just sitting by itself out alone in space. So yes, the energy level is some constant times the number of protons over n squared. So this really, I should say it's a hydrogen-like atom, hydrogen-like atom. If it's just hydrogen, then Z is 1. Okay, what next? What next? One and fixed, one and free. So in the one and fixed, one and free case, what we're really saying is, okay, the fixed end is a node, and the free end is an antinode. I'm going to draw, there we go. This side over here indicates that it's not fixed. So our first wave looks like that. There's my n equals 1. Our second has one antinode, and it has to have an antinode, or sorry, 2 antinodes, and it has to have one antinode at the end. There's an antinode here, there's an antinode here, around 1/3 of the way down L. Boom. And so on. So we'd have 1, 2, 3 antinodes. Cool. This is n equals 2, this is n equals 3. Traditionally, this is called the 3rd harmonic and the 5th harmonic, but again, I'm going to avoid the harmonic language just because it gets kind of confusing. All right.
So n is equal to the number of antinodes, regardless of whether it's both ends fixed or one end fixed and one free.
That's right. Yep, that's right.
Okay.
N is always equal to the number of antinodes in here. Okay, the relevant equation for the wavelength is lambda is 4L over 2n minus 1. So this thing on the bottom is always odd. So it's always going to be an odd number on the bottom. So like for n equals 1, I have just 4L over 1. For n equals 2, I have 4L over 3 as my wavelength, and 4L over 5, and so on. So I have 5/4 of a wavelength inside of my L. I have, in the case of n equals 2, I have 3/4 of a wavelength inside. And here I have 1/4 of a wavelength inside my L. One thing that tends to throw students for a loop on these kinds of one end fixed, one end free thing involves pressure waves and like a flute, say, or we had like a didgeridoo a while ago. So with pressure waves, the end that is fixed is the end that is exposed to the atmosphere. So if I have a side that is open, then pressure is fixed at atmospheric pressure. So this would be a fixed end, a node on this side. If I have a side that is closed to the atmosphere, then pressure is not fixed. Pressure is not fixed. And so for my standing wave, I'll have an antinode on the closed side.
So the closed end would be like a free end, right?
That's right. That's right. A closed end is like a free end in terms of pressure. Thanks for the question. Okay, I think that's all I really want to say explicitly for, I think that's all that really there is to say that's directly about standing waves. So one other thing to keep in mind, one thing about standing waves is we always want to remember our fundamental relationship between velocity, frequency, and wavelength. This is just a good one to keep in your back pocket all the time during 7C, because it's just, if I want to know something about the period, or I want to know about the frequency, or I want to know about the wavelength, I can translate really cleanly between all of them, knowing just these two equations. Okay, let me get the crying one if you're like falling asleep, and give me thumbs up if you're like still feeling all right about it, maybe lose the steam a little bit, and don't respond if you're sleeping already. Okay, all right, better than I thought, Some amount of sleeping already. It's kind of bimodal. Okay, either sleeping or wrapped. Okay, so I think that's all I really want to say for standing waves, unless there are more questions on them. Otherwise, I'm going to reference my sheet and see what's up next. Any quick questions? I'm going to grab one more drink of water in the meantime.
I have a quick question about the pressure example.
Go for it.
So the closed end would be like somebody's mouth on the instrument.
That's right. We treat that as being, so like practically, like if you play brass, it's like half the time your mouth is open, half the time it isn't. But in here, we treat that as being closed. Effectively, if you place your mouth on the side of the instrument, we treat that as closed. The pressure does kind of freely vary, in the sense that, like, if my mouth is like generating this pressure wave, it's the thing that is, it's the thing that is oscillating the most, right? My mouth has to be producing this wave if I put my mouth on one side of it. So that's kind of like where the source lives, where the thing that's bouncing up and down is operating from.
Got it.
Is that an okay answer? Does that
Yeah.
kind of clear it up? Or okay,
Definitely.
nice. Okay. I'm going to pop back over here. Okay, so to make myself feel good, I'm going to cross things off the list. Quantum mechanics, more or less done. Standing waves, more or less done. Qualitative descriptions of electric charge and force. Okay. So we just learned this today, right? I think it was a subject, or yesterday, right? It was like the subject of yesterday's morning session, maybe. So basically, as far as the qualitative descriptions of electric charge and force goes, we'd be looking for almost entirely your qualitative ideas. So here's some qualitative ideas, and I'll just throw them out there. See what you think. Okay, so the first thing is charge is quantized too. Charge comes in equal amounts, positive and negative, and just for fun, I'll make the positive side red. So it comes in quantized amounts, and that amount happens to be the same amount as the electron charge. So you can have a negative electron charge and you can have a positive electron charge. So charge comes in quanta just like the energy did in quantum mechanics. Anytime I have a charged object, it's really a super large number of, or not necessarily large, but it's some number of electrons or protons without, yeah. Okay, I'll try to keep it simple, that are generating that amount of charge. So electrons and protons, as far as we're concerned, are the only thing with charge. We're not going to worry about anything else. All right. So, okay. So electrons and protons, there they are. When I have two things which are oppositely charged, as any Garbo middle school meme will tell you, opposites attract. So there's a force that pulls these two things together. So the force that pulls these two things together increases as they get closer together. It increases as they get closer together. And it decreases as the amount of charge decreases. So I would say even this is beyond the level of what I would expect on the exam. However, I'll write it just for fun. So the force is proportional to the charge, and it's inversely proportional to the square of the distance. Yeah, so again, this is not on the exam. Not on this part, is not on the exam for sure. I'm looking only for qualitative knowledge. What else? I think in terms of electric charge and force, that's honestly pretty close to it. One fun fact about electric charge, which showed up in one of those videos, I believe it was a Patrick video on like a can. So one fun fact about charge is that when you put charge on a conductor, it will freely redistribute itself. So charge on a conductor will spread out. It'll kind of evenly spread out across the surface of the conductor. All right. Whereas charge on an insulator, let me make this visible. I realize that this is like way too small of text. The charge on a conductor will spread out, whereas charge on an insulator stays in one spot. Wherever I put it, it'll tend to stay there. It takes much longer for it to spread out. Okay. So it's not true that an insulator can't be charged. And it's also not true that a conductor must always be charged. Right? So whether something is a conductor or an insulator doesn't actually tell you if it can hold charge. It tells you about what the charge does once it's there. So anything can hold charge. It's just that insulators don't let it move very much on the surface, whereas conductors do let the charge move around. It lets it freely redistribute. One last thing while I'm here, corollary, is that if I've got two charges which have the same sign, there's a repulsive force between them. These two forces would be like the same size. So if I have two charges of equal magnitude, then they, they move each other with equal force. And in fact, they don't even have to be equal magnitude, right? You're still going to have the same force between them. But maybe that's a topic for another day. What else? I think that's kind of it in terms of like what I would deem exam ready for qualitative descriptions of electric charge and force. Any follow-up questions or things that weren't quite clear about that? We got chats coming in. Could you please discuss which is okay? So I've got questions coming in about potential energy and electric potential. What about charge related to voltage or potential energy? Insofar as we're doing qualitative description, no, I don't really think so. There shouldn't really be anything where you have to invoke equations. Looking mostly, this would be like a verbal response type thing. Yeah. For what it's worth, yeah, I think even like charges as sources of potential energy, I'm pretty sure that's left off explicitly in terms of the activities, but I could be wrong. So related to voltage or potential energy, I would say nothing quantitative, certainly. Does that answer? Is that all right? I don't know. I guess I'd have to go back and look at the exact details of the announcement. I can say like from here, I don't know what kinds of things I would ask that would be qualitative and also insightful. so as a practical matter, it's like I don't really see it happening. For fun, I'll say that so charges produce different voltage fields. Negative charges kind of act as like low points in voltage fields. Positive charges act as high points. And potential energy tends to decrease as positive charges approach negative charges and increase as charges are forced together. So yeah, so charges seek to minimize potential energy. That's why the forces point in the directions they do. Charges seek to minimize potential energy. And that's just that's mostly a general statement. Most things seek to reduce potential energy. I had another question going back for a moment, back to standing waves. Can I discuss which instrument we could consider two fixed versus one free? So the classic example of a one end or of two ends fixed instrument is a flute, because both ends of a flute are open. Flute. Also guitars, their strings are fixed on either end. Most other instruments that are blown, so like trombone or trumpet or whatever, if your mouth's covering one side, that'll be one fixed, one free. And again, we'll try to be fairly explicit about that. So I believe on a quiz when I had one fixed, one free, I said effectively closing one end, like the player puts his mouth on one side, effectively closing one end. It should be similar language to that. Okay. I'm going to call this one crossed. If there's more questions, feel free to drop them. In general, potential energy and force are opposite. So this is an interesting question. So I'll write it down. This is again one of those things that would not be, I don't expect you to do any calculations with, but force is the negative spatial derivative of potential energy. Yuck, what does that mean? Times the x vector, but we're not going to worry about that for now. So if you'll think all the way back to like 7a, I know it was a gazillion years ago, but there was this ugly thing. I kind of like it, but I'll say, I'll try to be popular. It was this thing. You remember this? The Leonard-Jones potential energy as a function of position. And if you'll remember, when you were to the right of this local minimum down here, there was a force that pushed you to the left. And when you were way over here, like riding this slope, there was a force that pushes you to the right. So in this sense, force is always opposite of the change in potential energy. Yes. So potential energy and force, like if you only gave me the potential energy at a point, I wouldn't know what direction the force was. I have to know how the potential energy is changing if I move to the left or move to the right a little bit. And the force will point me in the direction which reduces the potential energy, the one that pushes me down the slope toward the local minimum. Is that kind of answer? Is that all right? Nice. Okay, good stuff. Yeah, sure thing. Okay. What's up next? So we had diffraction was an interesting one, and interference, which are kind of related. And then Snell's law, lenses, and mirrors and beats are pretty much taking a back seat. So let's do diffraction. Diffraction, I think probably what we're talking about here is Young's double slit, right? Is that probably our main worry? So
Yeah.
what I'll do, question, I think.
I'm just saying yes. Yeah.
Okay, good stuff. Yeah, thanks. Okay, so what I'll do is I'll first just kind of give an overview of what the experiment was, because I think that tends to get lost along the way. And then I'll tell you what the equation is. And hopefully the equation will make a little more sense after I say what the experiment was. So let's do double slit first. I'll zoom in. Come join me in the zoomed in area. So first I will lock y'all to me. There we go. Okay. So Young's double slit experiment. What is it? What I do is I'm going to take some light. I'm going to take a laser. Let's make it a laser. It's got to be one consistent wavelength of light. So what I'm going to do is I'm going to take a laser. Meow, very cool. Nice laser, dude. And we're going to have this laser point at two slits in a wall. Okay. So the laser, for some reason, it's a very like wide laser. It's not very focused, but there we go. It's a laser. Okay. Because of this thing called Huygens Principle, which says that 2 points that are moving up and down produce circular or spherical waves in 2D. It's going to produce 2 circular light waves like this. Now, one of the main reason that this experiment is interesting to us as physicists is because it showed definitively that light has wave-like properties. If light were just a particle, then what I would expect is that the laser light would just go through in a straight line. Go through these, here we go, go through these 2 slits in a straight line. And if I were to put a piece of paper, a wall, on the far side, if I were to project the light onto that wall, what I would expect to see is just 2 straight lines. So if I were to just shoot particles, like if I just throw baseballs through 2 slits in the wall, I would expect them to just kind of roll over to the other side of the wall and hit, right? Like roll to wherever I hit them and stay there. What we found instead was a diffraction pattern. Whoops. Okay, it was a diffraction pattern. And there we go. So we found a really bright point in the middle, and then a bunch of other bright points linearly spaced on the wall. Huh, that's kind of weird. So why does this happen? Well, it turns out that this situation is identical to the situation of having like 2 speakers, which are wired in phase, and having a bunch of listeners sitting on the kind of like on the sidelines on this wall over here. So in some places, the 2 speakers, the 2 light sources, interfere constructively because the path length difference is such that, because the path length difference is an integer number of wavelengths. So when delta x is n lambda, that's when I get constructive interference. The total phase is an integer number of, an even number of pi, and this is constructive. Okay, so the reason this kind of logic flows is because the only difference, the only difference between these two light rays is the path length. There's no difference in phase because we're in initial phase because it's coming from the same source, and there's no difference in time or no difference in frequency because they're coming from the same laser. So the laser is producing the same frequency of wave throughout. Okay, let me pause for a second here and let me ask if there are questions about the setup. So motivation, why we care about it, what's cool about it, what we saw. And then I'll go through the equation real quick. Okay. If you're still typing, feel free to keep typing. Okay, so there's a problem set up. The cool thing about Young's double slit experiment was that it showed us that light behaves as a wave at least some of the time. Let me name some variables now. And once I've named my variables, hopefully this equation I'm going to write will make sense. We can approach diffraction-like interference problems. So yes, the thing is, for Young's double slit experiment in particular, the derivation is a little bit like convoluted, and we don't ask you to reproduce that for sure. It's like I said, it's like 5 steps, which is too much. So it is fundamentally a result of interference. Diffraction is fundamentally a result of interference, but we aren't going to ask you to derive it from what do you call it? A path length different, a phase chart, like you tried to do in class. Instead, if there's a Young's double slit problem, it'll just rely on the Young's double slit formula, which I'll go ahead and write here in just a sec. Okay, there are 2 alternative formulas that people like to use. One is d sine theta equals n lambda. Yuck. I don't like that one. To me, it's not intuitive at all. I don't know what it means. And I'll still explain what it means. I do now know what it means, but it's not very intuitive to me. The other one, which I think is much more intuitive and much more applicable, is delta y equals n lambda capital D over little d. Okay, so let me go ahead now. Now that we've got these, I can kind of like try to explain what each of these variables is supposed to be physically. So the first one is little d. Little d is just the distance between the 2 slits. There's little d. It's little because it's the smaller of the 2 distances involved in the problem or in the setup. Big D, capital D, is the distance from the slits to the wall, the distance from the slits to wherever we're projecting. Lambda is the wavelength of our laser. Wavelength of our laser. The same thing we've been using for lambda this whole time. Theta, which I really, like I said, I don't really love theta, but I'll write down what theta represents anyway. Theta is the deviation from a straight line extending from the middle of the 2 slits to the wall. So that's theta, like that. Theta is not super intuitive for me, but to each their own.
Wait, could you explain what theta is again?
Yeah, sure. So theta is this angle. It's the angle between the center or a line extending out from the center of the 2 slits to the wall, the central bright fringe on the wall, and it's an angle that points out toward a bright spot. Yeah, so that's important. So each of the thetas.
So it's the angle between a line that points from the center to the wall and a line that points from the
center
to the bright spot.
To a bright spot. Yep, that's right.
Does it matter which bright spot?
Yes, that which bright spot theta points to is indexed by n. So for each n, I'm going to have a different bright spot. Again, I don't prefer this upper one. It doesn't yield as much intuition for me, but the lower one I feel like has a nice physical meaning. So I'll give that here in just a sec. Okay, the last thing I want to say is this given notion of delta y. So delta y is a distance from the central bright fringe to some other position where I've got a bright spot. So both of these equations are talking about bright spots. Bright spots. Both of these equations are talking about bright spots. Each bright line in my interference pattern is represented by an n. N equals 0, n equals 1, n equals 2, and so on. Now these n are allowed to be negative. That's why I have lines both above and below my central bright fringe. Okay, so let's, with that in mind, let's take one more second to look at these two equations and see what they mean and get some intuition.
I thought that delta y was the distance between n equals 1 and n equals -1 if n is equal to 1.
Delta y is the distance between n equals 1 and n equals -1. So that's not true in general, no. So what I think what you might be referencing is this. So if I say just lambda d over delta, so if I get rid of that n, this is the distance between any two subsequent bright spots. Distance between any two bright spots.
Yeah, that's what I was trying to say. I was just trying to say, like, if n is equal to 1, then it's the distance between the n equals 1 and n equals -1 that you drew.
So so lambda d over little d would be between, for example, like n equals 0 and n equals 1. N equals 1 and n equals -1 would correspond to like two of these.
Yeah, yeah.
Okay, yeah. If that makes sense to you, then you're probably on the right track.
Okay, so if n is equal to, so we're doing distance between the two bright spots, one at n equals 1 and one at n equals -1.
So if you plug in n equals 2 to this equation,
Yeah.
the delta y you solve for is the distance between two bright spots. I like to think of this particular version of delta y being the same as the difference between the position of n equals 2 and the position of n equals 0. But in general, this equation just refers to the distance between, or the distance between any two fringes separated by like n-1 fringes. So here, if I plug in n equals 2, that's the distance from any fringe to any other fringe skipping a fringe. So like, if I plug in a 2 up here, that gives me the distance from the n equals 3 spot to the n equals 1 bright spot, which is the same as the n equals -2 bright spot to the n equals -4 bright spot. It'll be the same distance regardless of which ones I'm comparing between. Does that help, or is that still a little iffy?
So if n is equal to 1, it's the distance from the center to the n equals 1.
That's right. That's right. That's how I typically think of it. Yeah.
Okay.
That's right. If I were to plug in n equals 1, that would tell me the distance from the n equals 0 central bright fringe up to n equals 1. Good stuff. Thanks, Victoria. Okay. What else? What else? What else? Anything more on this? I've got a couple questions coming in. So theta depends on which bright spot. So it's interesting. Yeah, it's hard to think about dependence this way, right? So theta depends on all kinds of things. But theta, like if I solve back for theta using this equation, so it'd be what? Sine inverse of n lambda over d. All of the thetas corresponding to integer values of n are thetas where I get a bright spot. So in the sense of this equation, yes, theta depends on which bright spot. Yes. Theta is, we say it's indexed by n. So for any particular n we choose, we get out a theta corresponding to the bright spot. Does that answer your question all right, Isaac? So it depends on it in that sense, yeah. Nice. Okay, Aaron asks, does n always correspond to the areas of bright fringes with respect to the central fringe, or does it depend on whether we're talking about constructive/destructive interference? So I think probably what you're getting at might be that, like, sometimes in these practice quizzes we have like things that alter one side what do you call this? Alter one side of the interference setup. So like one of the slits has a crystal that changes the phase by pi/2 or things like this. So in that case, using this equation for bright spots would actually give you a location for dark spots. But this is like one of those minor things. It's kind of a niche thing. Assuming that the only difference between the upper and lower sources of light is path length, then these will always give you bright spots. Another question, can we measure from a dark spot to a light spot? So yes, sure. So if you measure from a dark spot to a light spot, because any two bright spots are linearly spaced with a dark spot directly in between them, if you measure from a dark spot to a light spot, this distance, okay, I'll draw it over here. So say we had a dark spot, then a light spot, and then a light spot, and a dark spot, and a light spot. So this distance is lambda capital D over little d for the two bright spots. The distance from a dark spot to the nearest bright spot is just going to be half that, lambda capital D over 2d. Does it make sense?
Can I ask about a specific question that was in the practice exam for like slit diffraction?
1 second, let me finish up the chats and then yes. Sound good?
Okay.
Yeah, I'll come back to you. Thanks, Victoria. Will we need to know any other equations such as tan theta equals delta y over d from dl, or are those the two we would use? Any question that I ask will be solvable using honestly either of these, but yeah, this combination should definitely work. Tan theta delta y over d, I believe that's just, yeah, that's one of the steps in the derivation, and we're not going to ask you anything about the derivation. Yeah. One intuition that I'd like to give while we're here, a couple of intuitions really, but looking down here at this lower one, delta y equals n lambda capital D over little d, this shows me that if I shrink the distance between my two sources, i.e. if I make the slits closer together, then the diffraction pattern will spread out more. So the tighter I make my slits, the more diffraction, or the wider my diffraction pattern will get. Yes, that makes sense. Okay, good. The farther apart I move my screen and my sources, also the bigger my diffraction pattern gets. And hopefully that makes sense kind of from like a projection standpoint. If you stand farther away from a projector, the image gets bigger. Finally, if I increase the wavelength of my light, wait a minute, does that make sense? Double check. Yeah, that makes sense. We're good. If I increase the wavelength of my light, I also get a wider diffraction pattern. I get bigger spaces between things. Okay, I have one more question coming in about this, which is, can you repeat one more time what n tells us in the d equals n lambda d over delta y equation? So the n tells us basically, or well, let's put it this way. The n assigns for us which bright fringe we're talking about. The n equals 0 fringe corresponds to the fringe which is closest to the two slits, the one right in the middle of them, the one that has 0 path length difference. The n equals 1 fringe and n equals -1 fringe are the ones right above and below that one. They correspond to, 1 lambda path length difference. So this referencing this guy. So if I look at like these two path lengths, I'll draw them both in black. Here's one path length to the n equals 1 line. Here's another. The difference in path lengths between these two lines, that line, is going to be equal to 1 wavelength. But like from an intuitive standpoint, each n just corresponds to a different bright spot. N equals 0 is the central one, the brightest one, and then n equals 1 is 1 out, 2 out, and so on. Okay, Victoria, let me get back to you.
Okay, so my question was about quiz, was under quiz 2, like the folder 2.
Sure.
And it was the second quiz.
Let me get a look at that real quick here.
Yeah, sure.
practice quizzes. Folder 2. Okay,
Yeah,
go for it.
and then quiz 2.
Quiz 2.
Yeah, I was just wondering, how come delta y is 2 centimeters and not 1 centimeter? Because I thought if n is equal to 1, delta y is the distance from the center to the n equals 1 bright spot.
Okay, a red laser, 700 nanometers, shines on a piece of black plastic with 2 narrow slits on it. The light then passes through the 2 slits and strikes a wall 3 meters away. The bright spots that appear on the wall are by 2 centimeters. How far are the slits in the plastic? So the question is, why is n 2 and not 1? Or
Why is delta y 2 and not 1?
Okay, sure. So in this case, because bright spots are separated by 2 centimeters, that
Yeah,
corresponds to, so for example, like the n equals 0 bright spot and the n equals
Yeah.
1 bright spot, this distance between them, delta
is
y,
2.
is 2 centimeters.
Oh, okay.
That's right.
So like the center is considered a bright spot as well.
That's right. The center is also bright. Good stuff.
Oh, okay.
Yep,
Thank
because
you.
the path length difference to the center is 0. Good. Thanks for the question. Okay, we got about 15 minutes left. Any follow-up last-minute questions on Young's double slit experiment? Okay, I'm going to move on back down here. I'm gonna actually tell you what, before I do that, let me get some thumbs. If you're like, yeah, I feel better about it now, let me see thumbs up. If you're like, I feel about the same as I did before, let me get like open mouth. And if you're like, I'm more confused than I was before, let me get crying. Crying, laughing, what is it? Okay, so it looks like that helped a little bit. Okay. It's hard to tell if no response means the same or worse or better. But okay. So the key thing, basically 2 key things about Young's double slit. The first is, intuitively, what does it show us? Young's double slit is an argument in favor of the idea that light is a wave instead of a particle. It turns out light's both, right? Sometimes it behaves as a particle, like in the quantum case, where it comes in a quantized amount of energy, hits a quantum state, and then bumps it to a higher state. Young's double slit experiment shows us that it behaves like a wave in some situations. Namely, it exhibits diffraction. It gives us a diffraction pattern when shone through 2 small slits. What the equation tells us, delta y equals n lambda capital D over little d, is it tells us the location, delta y, of bright spots relative to the central bright fringe on the wall as a function of n, an index, any positive or negative integer, lambda, the wavelength of the, what do you call this thing? The wavelength of the light, capital D, which is the distance between the slits and the wall, and little d, which is the slit spacing. Cool. I think that's it for Young's double slit. I'm gonna go and mark this one off. Okay, next up we got interference, then Snell's law. We kind of have to pick our battles here. Got about 10 minutes left. What I'm gonna do is I'm going to give a cursory overview of interference and how those what do you call them? Phase diagrams work, phase charts work. And then if there's time, we'll take a moment for Snell's law. Okay, so let's do interference for just a moment. Here's the deal for interference. The way interference works is I start off by assuming that I've got 2 sources of waves, source 1, source 2. These 2 sources of waves can be producing the same sound, i.e. the same frequency of sound, or a different frequency of sound. They also can be in phase or out of phase or partially in phase in terms of their initial starting point, whether they're initially kind of moving up or starting at a equilibrium and so on. That's the initial phase. Finally, anytime we talk about interference, interference must occur in space. So there needs to be an observer somewhere. Observer O over here. So the observer is the one who's listening to these two sources of sound. And here I'm calling it a sound wave, but in general, it doesn't have to be a sound wave. As we just saw, you can have interference of light. You can have interference like in the ocean. So interference can happen all over the place. There are two important, so let's just lay out all the variables. So source one has a wavelength lambda 1 and a period t1. Source 2 has a wavelength lambda 2 and a period t2. They can be the same, but they don't have to be. So they can have the same wavelength, same period, but they don't have to. There's also the notion of path length for each of these. So the path length is defined relative to the observer, or the part where you want to know whether you've got constructive or destructive interference. So the path length for S1 is just x1, just this distance through space. The path length for S2 is just this distance through space, x2. The path length difference, delta x, which we'll come back to in a second, is just the difference between those two path lengths. So this is the part that I think trips a lot of people up with interference, is that's what path length means. It's the difference between the two distances for our two sources. I've also gone ahead and implicitly assumed an order on delta. So here, when I say delta of any quantity, delta of mouse face, delta of mouse face means mouse face 2 minus mouse face 1. My drawing skills are limited on this. Okay, but so the point is 2 minus 1. That's what I mean when I say delta. It'll be source 2 minus source 1. So when I consider interference, it can be useful for me to draw in a phase chart. A phase chart tells me about the 3 differences in total phase, or differences in phase of a wave. There's 3 components to the total phase. The total phase is just the stuff inside the sine function. So a wave function y is like amplitude times sine of the total phase phi. The total phase, those terms, are just our 3 parts: 2 pi t over tau minus plus 2 pi x over lambda plus phi naught. So that's where the 3 columns of our interference chart come from. So we're interested in the difference in total phase, which includes the difference in 2 pi t delta 1 over t and 2 pi delta x over lambda. We'll put minus here. There we go, minus. So there's a negative sign here because typically in 2-dimensional space, waves expand outward, right? You don't have waves coming in like toward the source. They go away from the source, which corresponds to throwing a minus sign in front of the spatial term. And difference in initial phase, phi naught. Okay, now each of the elements of the row, this one down here, the differences from our 2 sources. So like, for example, 2 pi t of 1 over t2 minus 1 over t1 plus this thing, negative 2 pi delta. Wow, this is going to get really messy really fast. I'll zoom in. Negative 2 pi x2 over lambda 2 minus x1 over lambda 1 plus delta. So this will be phi 2 minus phi 1. These are both initial phases. Phi initial 2 minus phi initial 1 for our 2 different sources. That gives me, summing those up together, gives me the total phase. The total phase. Now, when the total phase is an even multiple of pi, this is constructive interference. So if the difference in total phase is 0, for example, that's constructive interference. When it's an odd multiple of pi, that's destructive interference. which means, so constructive interference means that the amplitudes of the wave add. In sound waves, this means that it gets louder. With destructive interference, it means that the amplitudes like subtract from one another. So it becomes quiet. I know that was kind of like a large, I don't know, that might be a little bit, maybe too theoretical or too high up. I know some of this we also did for FRQ1, so I don't want to burn too much time here if we aren't getting too much out of it. Do we have questions here or parts of this that make less sense than other parts? The two things I guess I would emphasize are, number one, when you're doing interference type problems, it's important to remember this. So that the total phase being an integer multiple or an even multiple of pi means it's constructive, and an odd integer multiple of pi makes it destructive. The other thing is just remembering to keep your deltas in order. So if you call something, if you say delta x is x2 minus x1, you have to keep that consistent across your other deltas too. Initial phase delta is 2 minus 1.
Can I ask about an example problem from the practice quizzes?
Tell you what, I'm gonna hold off for now. I can stay after for a minute or two.
Oh, okay, thank you.
But let me go ahead and real quick go through Snell's law, just because we got a couple more moments left. Okay, Snell's law. Woo! So Snell's law, basically, Snell's law is a result of oh my goodness, Fermat's principle. So Fermat's principle basically says that when you've got two media with different indices of refraction, different preferred speeds of light, n is c over v, where v is the velocity of light in the medium. So this is a good formula to have. If I've got light that enters one medium and then it hits an interface, which is where the medium changes from one to the next. If I have light that comes in and hits this interface, there we go. I call this angle relative to the normal the incident angle, and I call the angle that the light to which the light bends the refracted angle. So this is called refraction. So light bends because it wants to take as direct a path as possible when it has to move slowly. So as drawn, what I've shown here is a situation where n2 is greater than n1. So the higher the index of refraction, the higher the n, the slower light moves. So since the light is trying to take a more direct path to the right, more direct path, that indicates that n2 is larger than n1. If the opposite were to occur, so if I had light that came in and then bent away from the normal, in other words, the refracted angle was larger than the incident angle, that would tell me that n2 is less than n1. The light has sped its way over to get to the interface and now wants to zoom up and away. As a practical matter, the fundamental thing is really Snell's law. Fermat's principle is just kind of like a useful like moniker kind of. It's just a useful like metaphor. At the end of the day, the fundamental thing about refraction is Snell's law, which is that the index of refraction in the first medium times the sine of the incident angle is the same as the index of refraction in the second medium times the sine of the refracted angle. Boom. So given any three of these, the index of refraction, the incident angle, the second index of refraction, and the refracted angle, you can determine the last one. Yeah. If you don't have three of these, you probably need to look around in the problem and see if you can find other ways. Yeah, but so this is right a four, you have four unknowns. If you have three of them known, then you can solve for the last one. Okay. Questions on Snell's law? Happy to take some now. Let me look at the chat. Oops, I have an old one. How does it relate to interference? My fault. Hopefully I answered that, Colin. I'm not sure. Okay, so I know it's been a long hour and a half. I'm sure parts of that were, that couldn't have been entertaining all the time for everyone. So thanks for toughing it out. Hopefully it makes a little bit more sense now. At least one or two things have been clarified. And I'm going to go ahead and stop the recording here in just a moment. Before I do, are there any last questions that you'd like to document for all time, or at least for as long as YouTube's around, or at least until my YouTube account gets deleted or whatever? Otherwise, I'll go ahead and stop it and take any private questions. Okay, I have a question. Could you emphasize what part we should focus on most? Nope, not doing it. Nope, no bonus. You don't get bonus insight into the exam just for being here. Nope, sorry. But I would say I'm trying to cover most of the material fairly uniformly. Just want to clarify, optometry is fair game. I believe it's included in the covered activities. Yeah, it's in the covered activities. Optometry overall is kind of a minor part of 7C. So yeah, I don't plan on testing it in such a high stakes setting. Let's put it that way. It may appear on a future multiple choice quiz. Okay, I'm going to go ahead and kill the recording. If you've been joining us on YouTube, thanks, and we'll see you next time.